we want to use fundamental theorem of calculus to evaluate the following. The first one is the integral from 2 to 4 of x cubed plus x plus 2 dx. Let's start by anti-differentiating what's inside. What do we have to differentiate to get x cubed plus x plus 2? Let's look at it term by term. For x cubed, it's going to be x to the 4th divided by 4. For x, it's going to be plus x squared divided by 2. And for 2, we get plus 2x. And as I mentioned in the last video, when I introduced fundamental theorem of calculus, we do not need to worry about plus c because it's going to cancel out when we subtract the function evaluated at the upper bound minus the function evaluated at the lower bound. And we are going from 2 to 4. And the fundamental theorem of calculus tells you that the definite integral that we are given is just the change in this antiderivative as it's going from 2 to 4. So all we have to do is plug in 4 into this function. So we get 4 to the 4th divided by 4 plus 4 squared over 2 plus 2 times 4. And we want to subtract this function evaluated at 2. So minus the quantity 2 to the 4th over 4 plus 2 squared over 2 plus 2 times 2. And what's this going to get us? This thing is same thing as 4 cubed because you got 4 fourths up top, 1 4 down below. So you got 3 fourths multiplied to itself. And 4 cubed is 64. This is 16 divided by 2, which is 8. 2 times 4 also gets you 8. And minus, what do we have inside? 2 to the 4th divided by 4 is 16 divided by 4 or 4. 2 squared over 2 gets you 4 divided by 2 or 2. And 2 times 2 gets you 4. And what is this? You got 64 and 16, so that's 80. And 4 plus 2 plus 4 is 10. So that's 80 minus 10 or 70. That's our answer for the first one. Now let's look at the second one, B. We want to find the shaded area below. We know that our function is secant of x, tangent of x, and we are going from x equals to 0 to x equals to pi over 3. This graph is from Desmos.com, by the way. That's why it looks very nice. And we want to evaluate the definite integral from 0 to pi over 3 of secant of x, tangent of x, dx to find this area. And what do we have to differentiate to get secant of x, tangent of x? From our differentiation rule, we know it is secant of x, and we are going from 0 to pi over 3. Plugging pi over 3 into it, we get secant of pi over 3 minus secant of, plug 0 into it, 0. You know secant of pi over 3 is same thing as 1 over cosine of pi over 3, which is 1 over 1/2, which gets us 2. And secant of 0 is 1 over cosine of 0, and cosine of 0 is 1, so we have 1. So this area turns out to be 1, which can be fascinating. This area, which is bounded by this curve, trigonometric curve, which doesn't seem to be very rectangular and nice, but this area still turns out to be a very simple number of 1, which I personally think is interesting. Now let's look at part C. We want to find the shaded area down below. And you may realize since our function is even, the area to the left and area to the right are the same value. So we don't have to go from -2 all the way to 2. All we have to do is go from 0 to 2 of negative x squared dx, and we have to multiply this result by 2. What I'm talking about, all we have to do, instead of evaluating it all the way from here to here, all we have to do is evaluate from here to here to find this area and just multiply by 2 to get the entire thing. So what is this? We can get negative sign out of the way. So you got -2 times integral from 0 to 2 of x squared dx, or -2 times x cubed over 3 from 0 to 2, which gets us -2 times plugging 2 into it, 2 cubed over 3, which is 1/3, minus plug 0 into it, 0. So the answer we get is -16 over 3. And you may say, why is this negative? I thought definite integrals give you the area. And they usually do, not usually, and they sometimes do, when the function is non-negative. If you remember, what was definite integral? It was when we have this function, we draw a bunch of rectangles. That's one, that's another one, that's another one, and so on. And we have this width which is approaching zero, so we are having more and more rectangle, and we were multiplying this by our function value. And if our function value is negative, our width multiplied by this function value is also going to be negative. So our definite integral is going to be negative if our function is below the x-axis. So what's the area of this? Well, the area of this is just going to be negative of the definite integral to get us the positive value. So the area under the curve is going to be 16/3.